But without further ado, let's crack on our third session today for our seasoned presenter, Gideon, who has presented in since I've been running MQ Stream and probably even way before my time. But yeah, great presenter, and hopefully we will enjoy this session. There will be a feedback request at the end, obviously, but other than that, welcome to MQ Stream once again, and over to you, Gideon.
Okay, thank you very much. So yes, my name is Gwydion Tudor. I work in the MQ development team here at IBM Hursley and have done for many, many years now, and working on various different aspects of the product as well. And this session is going to be about Zero Trust and IBM MQ. So what we're going to talk about, essentially, we're going to talk about Zero Trust a little bit to begin with, a bit of a background, very brief background about what it is, what it means, and then move on to how this applies to MQ. And if there's time, there's a couple of extra things at the end as well that I'll look at in a bit more detail, although I know this is a 45-minute session, so it might be tough to squeeze all of that in, but we'll see how we go. Okay, so let's start off with essentially what is Zero Trust, a bit of a background about what we're talking about. So Zero Trust, it's a term that you've probably heard quite a lot about in the last few years, and it's gaining in popularity. It's a way essentially of thinking about security that moves away from focusing on the model that you might have previously had, which is static defenses based on your network perimeter. And if you like, you can think of that as having a moat around your important infrastructure that's inside your network, and you would, in the past, probably trust everything that's inside that moat. So everything that is running on your network, you'd implicitly trust it. However, that's not really good enough these days. So Zero Trust moves away from that model of trusting everything inside your moat and instead moves towards protecting the resources themselves. And with one of the important things being that you no longer use the network location as the main factor when you're deciding whether to trust a connection or not. And the key point, of course, as you probably can guess, based on the fact that it's called Zero Trust, is that nothing, whether that's a user or a device or an application, is trusted by default. So every access to a system or any kind of resource needs to be explicitly authorized. And that's very important. So why is this getting important? Why is this gaining popularity? Why do we need this? It's because this model of having a moat around your resources has been shown to not be sufficient, essentially, these days. There's been various breaches that have been quite widely publicized recently that have shown that it's actually quite easy for attackers to get past that moat. And so you can't necessarily trust everything that is inside your network. There's also a reason that systems are getting more and more dispersed these days. So you've got things running on the cloud, you've got lots of people possibly working from home. So you've got systems that need access to your core systems where MQ and so on is running that are not necessarily running inside that core network. So you essentially have lots of different moats these days. So it's getting more complicated anyway to have this moat model where you trust everything that's inside it. And finally, of course, even systems and people that are legitimately connected to your internal network cannot necessarily be trusted. There's always the insider threat problem that you need to also guard against. So those are all good reasons why you need to be moving towards a zero trust model these days. I probably should have said at the start, by the way, if you have any questions as we go along, then feel free to type that into the chat. I will read them as I see them pop up on the chat and probably take a break in the presentation to answer them if I can. Okay, so let's carry on with the presentation then. There's essentially three principles that Zero Trust breaks down into. So these are authenticate everyone, the principle of least privilege, and assume breach. So the first one, which is authenticate everyone, that one is, I guess, fairly clear. Given that we're talking about zero trust, now you cannot trust that any connections that come into your system should be implicitly authenticated. You have to authenticate every connection that comes in. So removing the implicit trust is the first thing that zero trust does. And by the way, the authentication that you do should be strong authentication. So user ID and a password by itself these days isn't considered particularly strong authentication. So you should be looking at multi-factor authentication ideally. Second principle is the principle of least privilege. So this is another one that's also been around for quite a while. And the issue here is that, of course, applications need to be granted authorization to do what they need to do. But when you're using a zero trust model, you should really be thinking about granting only the level of access that applications really need in order to do what they need to do. When applications or users need access to something, then they should have to go and request access for that resource. And of course, ideally, to prevent the issue of people requesting access that they might need in the future, even they don't actually need it right now, then that process of requesting access should be easy and straightforward when there is a legitimate need for that access to be given. And the final principle is to assume breach. So this is essentially having the mindset that a breach will happen at some point. It's not a case of if, but it's a case of when the breach will happen. And so you need to have the processes and procedures in place to detect that has happened and to limit the damage and to be able to recover from it quickly with the least amount of damage possible. So this essentially breaks down into two different things. And the first is to make sure that no one can get access to data that they're not authorized to see, even if they do manage to breach your authentication, for example, and get access to the system. And the way that we do that is with encryption. So you should be encrypting data at rest. And the other aspect is to have plenty of logging and auditing in place so that you're able to, first of all, detect that a breach has happened by looking at what's going on in these systems, and secondly, know what has happened during the breach. So what has been accessed, for example, by the bad actors. And that'll give you information about the scope of the breach and also let you know what to do to quickly recover from the breach and get things back to how they should be. And of course, attackers are continuously changing and improving what they do in order to try to get around everything that you put in place. And so you need to do the same and continuously evaluate what your processes and procedures are in order to keep your systems secure, and how you interpret these principles and put them into practice does need to be continuously evaluated and potentially improved as well, depending on what your evaluation decides. So let's move on, now that we've briefly introduced what zero trust is, let's move on to looking at how MQ comes into the picture here, what you can do in order to apply these principles to securing your MQ infrastructure. And we'll start off essentially by looking at what features MQ provides that allows you to secure your MQ systems in a way that will make you compliant with a zero trust model. So we'll start off with the authentication aspect. So what we need to do here is to authenticate all connections that come into your MQ network. And the three features that MQ provides that let you do this are connection authentication, TLS, and security exits. And we'll look in more detail at all of these later on. In brief, connection authentication is what lets your queue manager authenticate credentials that are provided by applications when they connect to your queue manager. So that could be a user ID and a password or a authentication token that's provided by applications. TLS, you probably know that TLS encrypts data on the network, but it also, given that there's a exchange of certificates when the TLS handshake takes place, it also provides authentication. So that's another mechanism for authentication. And the final is security exits, where if the other two features that MQ provides aren't quite enough or don't do exactly what you want, then you can supplement that with code that you either write or buy from a third-party vendor that does exactly what you want. To implement the principle of least privilege, which is essentially setting authorization on everything that can be accessed within your MQ estate, then MQ does provide authorization controls that you can set. And we'll look again in a little bit more detail about that later on, but it's there essentially as well. I'm going to say on this slide, it gives you the ability to set authorization controls on pretty much anything that you can do within MQ. And of the last principle of assume preach, which of course breaks down into the two aspects of, first of all, encrypting data. So you've got options here of using TLS to encrypt data when it's on the network, when it's being transmitted between your MQ endpoints, and also AMS or disk encryption, which is how you can encrypt messages when they're at rest. So AMS is what MQ itself provides, which gives you end-to-end encryption from the moment that the message is put by an application into the MQ network right up to the point when it's got by the application that eventually gets the message off the queue. Disk encryption is not an MQ feature in its own right. It's what you can do using your hardware and operating system, and it provides slightly different capabilities to AMS. Again, we will look at that in more detail later on. And on the auditing and logging side, there are auditing and logging messages produced by MQ, which lets you know what's going on in your infrastructure, both on the queue manager itself and also application activity trace, which tells you what applications are up to as well when they're connected to your queue manager. So that was a high level overview of the facilities that MQ provides that let you secure your MQ estate. So we'll look at each one now in a bit more detail, starting with the authentication. So we want to authenticate every connection that comes into the MQ network. Now, there's actually quite a lot of places where that needs to take place. So first of all, it is, of course, essential for all applications that connect into your queue manager. So those applications could be running locally on the same system as your queue manager, or they could be running remotely and connecting in over the network. Regardless, if you're genuinely want to move to a zero trust model where you actually trust nothing until it has actually explicitly authenticated, you need authentication for both those type of applications. And of course, those applications could be connecting to your queue manager in order to do messaging, or they could be connecting to do administration. So we've got a screenshot there of the MQ Explorer on the left, just right underneath the client application, which you can assume is a business application, for example, doing messaging. An example of two different applications that can connect to your queue manager. They're both applications, however, they connect for different purposes. One for doing messaging and one for doing administration. They both need the same level of authentication when they're connecting to the queue manager. There's other places as well where you need authentication, including some of the newer ways of connecting into MQ. And that is the features that have been added recently to allow you to interact with MQ over HTTP. And that is the MQ console, which is a browser-based interface, which lets you administer MQ, and also the REST API, which lets you both administer and do messaging over HTTP. Now, all those endpoints connect into what's known as the MQ web server, which is essentially another application that provides the HTTP endpoints that supports the REST API and the MQ console, and then connects to the queue manager. So there's authentication that needs to take place there in order to connect into your MQ web server. So that's logging into the MQ console or logging into the REST API. So you need to take care of that. And also because the MQ web server is essentially another application that's sitting there in between your HTTP endpoint and the queue manager, that the authentication also needs to take place between the MQ web server and the queue manager usually. And the other place where you need to think about authentication is when you've got a queue manager talking to a queue manager. Now, you might traditionally have not cared so much about this. You might have assumed that if there's a queue manager running on your internal network, then it should be trusted because it's one of yours. So why wouldn't you? But again, if we are going to be rigidly applying a zero trust model where we don't implicitly trust anything that's on our internal network, you still need to have authentication on those channels between two queue managers. So let's look at the features that MQ provides to do that in a bit more detail now. So let's start off with by looking at application security. So applications connecting into a queue manager. And the first feature that MQ has that lets you authenticate applications that connect to a queue manager is called, surprisingly enough, connection authentication. So what this does is to let you configure your queue manager to require that applications that connect in, whether they're local or remote applications, supply some kind of authentication, some kind of credentials when they connect into your queue manager. Now that could be a user ID and a password, or it could be, if you're using more recent versions of MQ, an authentication token. And those credentials, when the application supplies them, will be validated by the queue manager against whatever user repository has been configured on the queue manager. So that could be the local operating system, or it could be LDAP, or if it's an authentication that's provided, then the token in its own right essentially can be checked by the queue manager without needing to go to an external repository. And of course, if the application doesn't provide anything, as is the top example there on the right, then it's not allowed to connect because you've configured the queue manager to require that authentication credentials are provided by the application. Now, of course, I mentioned earlier on that yes, you do need to specify, you do need to send credentials when the application connects, because you really should be requiring that everything that connects should be authenticating, but you also need to make sure that it is strong authentication these days. And user ID and a password doesn't necessarily cut it these days. Customers definitely want to be moving to stronger authentication mechanisms than that, such as multi-factor authentication. And one way that you can do that with MQ is to use the fairly new feature of token-based authentication. Now, this is only available on distributed platforms at the moment, so not ZOS. But what you can do when you have a queue manager that's configured to do this is that the client application can obtain a token from some kind of centralized token issuer. So we've got Keycloak, for example, in this picture. There are many others available. And that token is different to a password in that it can be time limited in its validity. It's not necessarily, or it's a less sensitive piece of data. So instead of having passwords flowing across your network, which you might not necessarily want for security reasons, you've now got a token being sent from the client application to the queue manager, which is only going to be valid for a certain period of time. And the type of tokens, by the way, that MQ supports are JWTs, which are JSON Web Tokens. It's quite a widely adopted industry standard by now. So the benefits of token authentication, I've mentioned one of them, which is that you don't have passwords flowing across the network anymore, you've got tokens instead. The other is that you can centralize your identity management, essentially, that you have a token issuer that's used by your organizations. And instead of having user ID repositories spread across all your systems, you've now got a centralized place where you manage that. Now, the way that the token is validated by the queue manager is that the queue manager checks that the signature of the token matches the keys or the certificates that have been loaded into the queue manager's key store. So there's no communication between the queue manager itself and the token issuer, but the queue manager already knows what the valid keys are that would be used by the token issuer, and that's how it checks the validity of the token. Now, that does mean that there is a little bit of setup required in that you need to load the trust store that used by the queue manager with those keys or certificates from the issuer, which is a little bit of work, but you can get around that with the more recent enhancement, which is JWKS support. What this adds to the token authentication feature is the ability for the queue manager to talk to the token issuer in order to request the keys or download the keys that are used by that token issuer to sign tokens. There's a little bit of setup needed, of course, in order to tell the queue manager where to go to connect to the authentication server and to set up the certificates that's required for the HTTP requests that are made by the queue manager. But it does simplify things in order in the way that you don't need to keep updating the keys in the trust store that's used by the queue manager that are used to sign tokens. So that makes things even easier if you're using token-based authentication. So moving on to another feature that MQ has that lets you do authentication, which is TLS. You're probably all familiar with the fact that TLS does encryption, and as I mentioned, TLS also does authentication when it's configured to do so. So the server will always, and the server in this case is the queue manager, the queue manager will always provide a certificate when a client or another queue manager makes a TLS connection to it, but that client can also provide a certificate. So when they both provide certificates to each other, so there's an exchange of certificates during the TLS handshake, then the client and the server can both authenticate each other essentially, so they know that they're talking with a trusted partner. Now, there's a few things that you need to configure in your queue manager in order to make this happen. Of course, they both need to have certificates, and they both need to trust each other's certificates. So that might be because you've swapped the certificates between the key stores, or more likely you have added the CA certificate of the CA that signed the queue manager and the client certificate to the key store on the queue manager and the client. And you need to configure the channels to use TLS and to also require TLS authentication. So that SSL-C auth parameter on the channel definition that you can see in the bottom right of the slide, that is what tells the queue manager that it needs to request a certificate from the client for the TLS handshake to succeed, and it needs to be provided by the client and, of course, be trusted in order for the handshake to succeed. And the final thing you can do to limit who can connect using TLS is to also require that the certificate that's provided by the client or the queue manager that's connecting in has a certain value for the distinguished name. So that's the SSL peer attribute there on the channel definition. That's one way to do it. You can also use what are known as channel authentication rules, which are actually more fine-grained, so better really than just setting the SSL peer value on your channel definition. They let you define that certain connections where the distinguished name of the certificate or the issue of the certificate match a certain value can be allowed or can be blocked based on those channel authentication rules. And that's how you make sure that the connection is coming in with a trusted certificate from a trusted partner and exactly the user or the person or application that you expect to be connecting in over this channel. So those are the two built-in features that MQ has for authentication. If that's not enough for you, then you can augment those with security access, which is a feature that MQ provides to allow you to add additional checks or separate checks to what MQ provides itself. So you can write your own code that does whatever level of checking that you want, or you can buy security exits from third-party vendors as well. And the exits can actually exchange data, a pair of exits, the two ends of the connection can exchange data between themselves before they are satisfied that the connection is trusted and allow it to go ahead. So in summary, on the authentication side, these are the three ways that you have of doing it in MQ. You have a connection authentication, which checks credentials of applications that come in. You've got mutual TLS and you've got security exits. Now, those are the options that you have for applications connecting into your queue manager. Now, also remember the other type of connections that you could have coming into your queue manager, other queue managers. And typically you might not have been authenticating those connections in the past, but in a zero trust world, you really should be authenticating those these days. And the options that you have for doing that are essentially a subset of what I had on the previous slide for applications. It's simply mutual TLS and security exits for connections coming in from other queue managers. Now, everything that I've talked about in detail so far has been about authentication connections coming into a queue manager. But remember, there are other ways of connecting into your MQ infrastructure, into the more recent additions to the product, shall we say, which is the MQ web server and the MQ console and the REST API that it provides. And in this case, the application that is connecting in to the REST API, say, or a user that is logging into the MQ console is authenticating with the MQ web server, not with MQ. So the important point here to remember is that completely separately from what you already set up on your queue manager in order to ensure that you've got authentication turned on for every connection into your queue manager, you also need to do the same on your MQ web server to ensure that every user ID or every user that connects to your REST API or your MQ console needs to authenticate. And the way that you do that is in the MQ web server configuration. So MQ web server is actually a Liberty server that is bundled with MQ. And so you just need to edit the configuration of that server in the XML file that contains all the configuration. And any of the mechanisms that Liberty supports can be used for authenticating your user IDs. So your users, the connections into the REST API. So that can be user ID and password, it can be client certificates, or it can be OIDC or anything else that Liberty might support. The key point here is that you need to think about this if you're using the REST API or the MQ console, in addition to everything that you set up on the queue manager. Okay, that was authentication. We looked at that in a fair amount of detail. We'll move on now to the principle of least privilege, which, if you remember, is granting only the level of access to anyone or anything that is connected to your MQ estate, only the level of access that they actually need in order to perform the operations that they need to do. Now, before we look at exactly how you grant authority to user IDs to do something in MQ, we need to make sure that every connection actually has a user ID, because the user ID is what you use in order to grant access. So in order to make sure that every connection has a user ID, we need to map a connection that's been authenticated to a user ID. Now, there's different ways of doing this, depending on how the application has connected. If the application, well, actually, depending on how the application has been authenticated. If the application connects and authenticates using connection authentication, and that is, it's provided a user ID and a password or an authentication token when it connected, you might want to use the user ID in the credentials that the application sets. So if I log into the queue manager and give the queue manager the user ID Gwydion and my password, then you might want to adopt that user ID for the lifetime of that connection. So all the authority checks would be performed against the user ID Gwydion. Or similarly with token authentication, there is a way to there is a way for the token to have a user ID claim within that token, and that can be adopted by the queue manager. And it's this adopt context parameter or attribute in the connection authentication configuration that you need to set to yes in order to tell the queue manager to do that. The other option that you have is if the application is connected in using mutual TLS or as authenticated by giving a certificate when it connected in using TLS, then you need to somehow map that certificate that's been provided by the application when it's connected in to a user ID that can be used by the queue manager to authorize operations that connection performs. And the way that you can do that is, I think, pretty much in order of preference here. Firstly, using channel authentication rules, because they can be used in a fairly fine-grained way to map connections that provide a certain certificate. So you can base it on the distinguished name of the certificate that's provided and map that connection to a user ID based on what you've used to map it off. So that would be, for example, if a certificate, if a connection comes in and provides a certificate that has a distinguished name with Gwydion in it, then we can map that to the user ID Gwydion on the system, and then use that user ID for authority checks from that point onwards. You have other options, which are to use security exits in order to assign a user ID to the connection, and also the MCA user on the channel definition. That's probably the least preferred option. That is on the channel definition, and therefore any connections into that channel that are successful will use the same user ID, which might not be what you want. And the final option that you have is if you're using security exits to authenticate connections, well, actually the security exit itself is able to set the user ID that is used by the channel for the lifetime of that connection for authority checks. Now, once you have a user ID assigned to the channel, now that it's running, it's fairly simple to grant authorities to that user ID to do whatever that application needs to do that is connected to your system. So we start off by looking at applications that want to do messaging. Then you can protect access to MQ resources. So these would be queues and topics most commonly, but there are other resources available. And also, you can grant access to only the applications that you want to be able to set the context of messages. So the context of messages is the information that you find in the message descriptor. It's the user ID that put the messages and things like that. Usually applications don't need to change that, which is why they need a higher level of access in order to do that, something that you need to explicitly grant to the application. But you are able to grant that level of access if you need to. So that's all controlled using the authority checks that you can set up in MQ. On distributed systems, you have the set MQ and the set authoreg MQSE commands available in order to control your authority records. On ZOS, it's done slightly differently because you can use BRACF profiles or whichever security manager that you're using to control to control access that you're giving to certain resources in MQ. Now, that is applications that connect into your system in order to do messaging. Of course, there are other types of applications that connect into your system, and these might be applications that connect in order to do administration. So your MQ Explorer or your MQ console, for example. Now, these applications still need to be able to connect into your system. They still need to be able to put messages into command queues to issue commands. So everything that I mentioned on the previous slide about granting access to queues and so on is still relevant at this point. But on top of that, in order to actually issue a command that changes something or displays information actually about resources in your queue manager, they need to be granted access to issue those commands on certain resources. So again, you can, in very similar way, grant access for user IDs to perform administrative actions by issuing commands on objects in MQ. You can actually grant very precise authority to, for example, define a queue with a certain name, things like that. Now, we talked about the MQ console and the REST API as well, and the fact that you need to set up authentication separately for your MQ console and the REST API, because this is in the MQ web server. You also have an authorization to consider here as well. And the way this is performed by the MQ console and the REST API is that they use role-based authorization. So each user that connects into the REST API or the console has to be granted access to a role. There's 3 roles that are available in MQ. There's the MQ web admin, the MQ web admin read-only, or the MQ web user. I won't go into all the details because of time about what all those different roles are, but each user needs to be assigned into one of those roles, and which role they are in will control which user ID is used for the authority checks that are carried out for the actions that they perform. An example is if I log into the MQ console as the user ID Gwydion and I'm in the MQ web user role, then actually every action that I then perform, whether it is opening a queue for messaging or issuing a command to alter a queue to the MQ console, that will cause an authority check to take place on the queue manager for whether the user ID Gwydion is allowed to perform that action. But you do need you need to configure that in the MQ web server and also consider how it interacts with the security setup on your queue manager. So the final principle is assume breach. So this is having the mindset that a breach will happen at some point. It's not a matter of if, but when, and being prepared for it. So there's two things that it breaks down into. First, which is collecting audit logs, and the second is encrypting data so that even if someone does get hold of your data, they can't do anything with it. So we'll look briefly at what auditing facilities MQ has to start off with. So MQ on ZOS and distributed works slightly differently in this case. If we look at security, for example, on ZOS, it's the security manager, which is RACR for whichever product you're using, that logs all access requests to resources. So every application or user ID that tries to open a queue or issue a command. And on distributed, because this is there aren't any calls to an external security manager taking place here. It's MQ essentially that records the access attempts here, but there is a way on both platforms in order to record authority events. There are also other types of events that are recorded by the queue manager on both sets of platforms for any configuration changes that take place. So command events and configuration events record any commands that are issued against the queue manager, and also let you have a snapshot of what an object was like before and after a command was issued in order to change it. So you have that information available if you have your queue manager set up in order to produce those events and you consume those events off the event queue where they are put. So you can use that information altogether to be able to see what impact a breach has in order to maybe detect early on that a breach has happened or that even someone is attempting to breach your systems. If you have that data being collected and analytics in place to make sense of that data. And the other thing that you can do on the distributed platforms is to use application activity trace in order to get a view of what applications are doing when they're connected to the queue manager. So all the API calls that applications do when they're connected to your queue manager are recorded by this. And also don't forget the MQ error logs. So whether you're running on ZOS where messages are put out to the MQ job log, or on distributed where you have the queue manager error log, there are messages output by MQ for all sorts of things that happen, such as channels starting and stopping, or problems with TLS handshakes, or not all, or applications and user IDs trying to access objects that they're not authorized to. You can also, of course, forward these logs to some kind of centralized place, Kibana, for example, where you can keep them and then visualize them better and maybe do some analytics to get a better feel of what's going on your system. Going a little bit quicker now, because of, if you haven't noticed, because of the time, we're getting close to the end now. The other aspect of assuming breach and making sure that you contain the impact of any breach is encrypting your data. So AMS is the feature that's provided by MQ in order to provide end-to-end encryption of your message data. So from the point that a message is put to MQ to the point where it's got by the intended recipient of your message at the end, the message stays encrypted, both in memory, on disk, and when it's on the network. And the performance impact when it's configured to only encrypt your message and also reuse the key a few times for subsequent messages can be actually quite low, similar to TLS, for example. The key point here is that this should be transparent to applications. You don't need to change your application at all, and they don't know that AMS is being used. It just transparently encrypts the messages and makes sure that even if someone does get hold of your network traffic or the data on the disk, so that's stored by MQ, they won't be able to read your messages unless they are actually the intended recipients and they have the keys to decrypt those messages. The alternative to that, if you want to encrypt your messages at rest, is to use disk encryption. Now this has pros and cons compared to AMS. It might be simpler to set up, but it doesn't, of course, protect your messages when they're in memory or when they're on the network. It only protects essentially against your disks being stolen. And the performance impact, the performance characteristics are slightly different because instead of the message being encrypted once when it's initially put into MQ, you're now having data being encrypted and decrypted on each disk read and write operation. But MQ does work with encrypted disks as long as it's transparent to the application, so transparently to MQ essentially in this case. And also on ZOS, there is support for encryption that's provided by ZOS itself and the disk subsystems. So there's a comparison here on this slide on the different types of encryptions that are available to you in ZOS. So you've got TLS, that's only for the network. You've got dataset encryption that's provided by ZOS as part of its pervasive encryption. And you've got CF encryption as well for encrypting messages on shared queues. All do different things. You can use them together to have your messages encrypted at rest and on the network. However, pros and cons there against using AMS or that pervasive encryption, because only AMS provides you the end-to-end encryption that comes with MQ. The others do slightly different things and might not protect you against the same things. Quickly talk about quantum because this is a consideration these days. So the algorithms that are used for encrypting data, whether it's TLS or AMS or anything else where you encrypt data, either using public-private key encryption or symmetric key encryption, those are increasingly becoming vulnerable to quantum computers being able to break those algorithms. Now, it's not necessarily a problem yet because quantum computers are still pretty much in their infancy, but they are getting better and better. And IBM is one of the companies that are putting a lot of effort into research on quantum computers and has a target of producing a quantum computer with thousands of logical qubits in the next few years. Now that starts to come into the realm of being able to break some of the encryption algorithms, some of the asymmetric encryption algorithms that are used by things such as TLS and AMS. Not yet a problem unless you consider the fact that there are probably people out there that are storing data that is sent over the network now in order to be able to decrypt it in a few years' time when these quantum computers become available. Also, because this might well become a problem in a few years' time, you might want to consider it now in order to make sure that you don't get surprised in a few years' time. I do realize that I've reached the end of the time. So this is a case of just using the correct algorithm that is going to keep you safe in a quantum world. So I will skip on to the summary and just say, sorry, that I wasn't able to do all of that in 45 minutes. I really didn't think that 45 minutes would be so short. So we've introduced Zero Trust, said why it's important. There are all these features available in MQ that let you secure your system. Make sure that you make use of them with the zero trust framework in mind of actually authenticating everything and locking down everything as much as you can, and have those processes in place so that you do assume that at some point there'll be a breach and that you know what to do when that happens in order to limit the impact and recover from it. Thank you.
Thank you so much, Gideon, and thank you very much for a very insightful presentation. No problem for running too long, and it's a shame that it's 45 minutes. It is very short, to be honest, but it was very useful. And there is quite a bit of information online on zero trust, so I would recommend people just reading through the overall principles for zero trust. And this is a great way. This was a great presentation to actually align it to MQ and how we run MQ. So it's great. Thank you very much. Anyone, if they have any questions now, they should be able to unmute themselves. But if not, as I say at the end of the any presentation, Gideon has agreed to take questions directly, which is in the agenda. You can find his contact details, so via LinkedIn or personally in IBM account. You can send your questions. But just quickly, anyone has any immediate questions now? Doesn't seem so. So, Gideon, once again, thank you very much for your presentation. People thanking you in the chat as well. It was very informative, really good. Appreciate you always submitting sessions and presenting it in the conference. So thank you for your time very much. And let's wrap up. Yeah.
Okay, no problem. Thank you all for coming.
Thank you all. Cheers all. Bye now.
Bye now.
Bye bye.